Yes, we have only 5 students in our classroom. So these are important topics. So I'm very much disappointed that only 5 students in our classroom. You all know that examination is going to be face to face. Therefore, you have to learn those topics. As you know, my examination principle is such that you can use all books, notes, everything, not computer, not cell phone. However, okay, we are still continuing DC to DC converters. As you know, DC to DC converters are widely used in communication technologies, plus in electric vehicles, plus in electrical energy production, such as photovoltaic cells. They produce DC voltage, and if you want to control the DC value, you have to use either you have to reduce the voltage or increase the voltage. Therefore, it is necessary. And it seems that direction is towards DC, since control of DC is now possible. In early 20th century, it wasn't possible at that time. Just a moment, it's a bit cold. Moment. I close the window. Okay, now we are starting. You remember that we have discussed normal DC to DC converters, and we came to the buck converter and boost converter. That is the picture you remember. We are comparing that analog, high frequency sawtooth waveform, triangle waveforms, with this control signal, and the intersection is giving us turning on and off times. And on time is kT, and off time is 1 minus kT. That one is total period. I continue. We have derived those equations last week. We have seen step down, step up, and also we have seen those quadrant operations, mainly the 4 quadrants. First quadrant equations, second quadrant equations, and also third quadrant and fourth quadrant operations. This is a typical a DC machine drive system as well, and you can control the machine from S1, S2. If you use S1 and S2, the current is going to flow like this, in this direction, as shown here. But if you run, instead of S1, S2, if you run S3, S4, current is going to flow like this. So for motoring in this direction, in positive rotation, let's say, for motoring again, it's the third quadrant, that S3, S4 are operating and then running the DC machine in opposite direction. Okay, and of course um, those diodes, these are called feedback diodes, or sometimes it's called freewheeling diodes. Those diodes, since you cannot convert current immediately in your inductance, so when you switch those main switches off, then current is going to continue to flow. We described those in detail anyway. You already know that. And then last week we have studied the buck converter. You remember that. For the buck converter, that's the main circuit. The current is going to flow. When you put this switch on, current is going to flow through that direction to the load. And since you have a source here, current is going to rise. You can see that. And then when you put it off, you already charge your capacitor, which is parallel to the load. You can see that. I just repeat last week's course material. Then, of course, the capacitor, which is fully charged, then is going to continue to give current to the load. That's why we represent the current flat. But input side, current is fluctuating, and it's a maximum value and minimum value, and you can. This one is a capacitor current, by the way. Capacitor current is fully charged and discharged, charge and discharge. But what we actually need, this one is the inductance current, that one. What we need actually two things. Delta I should be limited and delta V should be limited. Particularly delta V is a critical value since the output might be a delicate electronic device, communication device and things like this, and the voltage fluctuation should be limited. I have already driven those equations. You know how to those equations. Output is a typical buck. Output is equal K times Vs. K times Vs means if you put on time longer, then your output is going to be approaching to K is between 1 and 0. If K is 1, that means you are already sending all the input to the output. But if you put some chopped part of it, assume that K is 0.5, then you are sending half of the input to the output. Half of the input is sent by to the output. Delta I is the ripple. That is the equation, and we have driven those equations. You can see that I have explained those to you. Delta I. And also we have already seen how delta I is here, is driven here. And also we have seen the output current as well. How much output current will change. Whatever the voltage ratio is, the opposite is the current. Don't forget that. Since voltage times current, and also we have calculated delta V is a function of capacitor and also the period here, or if you put it the bottom, frequency, so inversely proportional with the frequency. And delta I is also affecting delta V as well. So the delta V should be as low as possible. And I remember I solved the problem. Those equations I have driven to you together with you. And this is what we are going to do right now for step up or boost converter. Delta V, for example, is the function of square of F, and also these are critical values, by the way. That is critical value of inductance, and that is the derivation of those equations. I've just warming up. Last week we have discussed that one, and I remember this is a critical value of the capacitor, and I remember I solved the problem to you. This is the problem I solved. Okay. Now, boost converter we are going to study. Today our topic is boost converter. We have now in our classroom only 8 students. Only 8 students. In 20 past 9, which is called academic time. Nobody is allowed to get in the classroom after 20 minutes, although I allow you. Not here. If it's a face-to-face course, I allow the students, considering the traffic of the Istanbul conditions. However, here is a computational electronic link, therefore there is no excuse of traffic. So in 20 minutes, 20 past 9, students will be considered as late. Sorry about that. Just a moment. Okay, now we are starting. Yusuf Selim, right. Muayet, Ahmet, Kasım Doğukan, Ener Gezer, Bulutan Kaplan, Batuhan Berat ve Abdulbari Abdulbaset are with me. Thank you for attending and listen carefully. It's simple. Now look at the circuit first. I'm going to make it a bit bigger. Yeah, look at the circuit. There is whenever you see a circuit, always look at first which one is the controllable electronic switch. This MOSFET is the controllable switch. If you give a gate signal, it turns on, providing that it's drain and source voltage. That one is drain, that point, and this one is source, or anode cathode, you may call it if you want. If it is positive and if it receives a proper gate signal, it turns on. Okay, so when it turns on, what's going to happen? This inductance is actually short circuited with source, inductance, and current is going to flow here. Whatever happened here, nothing. If that capacitor is fully charged, then capacitor is going to supply the load, which is the case. However, here we are now circulating the current, and there is no resistance to limit the current, and current is going to rise linearly. Switch is in one condition. Current is going to rise linearly. That is the case. Okay. That current here, the capacitor current, is reference, by the way. In actual fact, in this direction, current is in this condition. Supply, since the voltage reference here plus the current is going to be in this direction. Onu da göstereyim. 5 punta tabii çok alan. Biz 2 puntaya insek iyi olacak. Evet. So current is in this direction. Flowing like this. But the major current rise is occurring here. That load has got a continuous current, and the capacitor is providing. You can see that this is a capacitor current. capacitor is providing that current, negative. Okay. With respect to its reference value, it's negative. As far as load is concerned, it's a positive current. So this is the capacitive current. But no current we get it from supply. And in the meantime, current is rising from a minimum value to a maximum value. Minimum value is I1, maximum value I2. And if you look at the voltage, sorry, I couldn't see that one. Voltage U. Voltage U'yu bakın nerede tanımlamış, göstereyim de. Voltage U dedi, burada tanımlamamış. Sağ olsun Muhammed. Ama bunu söyleyeyim size. Burada yani şu iki nokta arasındaki gerilim, between that point and that point, voltage is zero. Neden? Çünkü you are neglecting the voltage drop of this switch. So current is flowing through that line and rising. Current is rising. Supply current, you can see that. And of course in inductance as well, the same current is rising. Then when the peak point reached, we are taking that switch from 1 to 2. In other words, we put this switch off. We put this switch off. So what's going to happen? You already store energy in your inductance, and you already have got a source. Since the slope of this current is negative, so VL is equal L di dt. Bağlamamış. Evet. Evet, kalemi bağladım. VL is equal to L di dt. Inductance voltage. That voltage. So since di dt is negative, current is reducing, but the current is going to flow to this part. Some of them is supplying the capacitor, some of them is going to, but voltage here, the capacitor voltage, which is VC, is together VS plus VL is higher than VS. So you already know how step-up action is all about. So output voltage, this voltage, output voltage, it becomes higher than the input one. That's what step-up action is all about. But if you look at the rest of the network, that is the case. Current is flowing like this, and VL plus VS is equal to VC or V load, VA, which is higher than supply. In the meantime, by the way, since we are charging capacitor, the capacitor voltage is rising from minimum value to maximum value. However, since the stored energy in your inductance is used, current of the I1, this current, göstereyim hangi current olduğunu. Şu current, that's the one. I1 is getting down. That's the one. Of course, that current, the capacitor current also is reducing since capacitor is also charged, but in the meantime, the energy in inductance, some of the energy in the inductance is discharged to capacitor, some of them together with the supply going to the load. Therefore, current in capacitor current goes down and the input current goes down. And when the period ends, you put your switch on again. Your control switch on and again. Biraz daha küçülteceğim. Hepsi biraz daha fazla şekil görün diye söylüyorum. So if you understand the basic principles of it, you are actually storing energy in your inductance. Ana devreden göstereyim. Şunları sileyim. Hepsini. Yeah. When you put the switch on, follow my cursor, please. Current is flowing like this, but in the meantime, current also supply the load. Current, assume that load current is continuous. However, the capacitor voltage goes down, reduces, discharge, of course, but this inductance current rises, inductance energy rises, and then when you put this one off, then this circuit occurs, and the energy flows to the capacitor as well as the load. So that is what step-up action is all about. But without proving, without deriving the analytical equations, this is only sayings. But never forget that from that point, from this point to that point, which your switch is on, is kT time, and between from that point to that point is 1 minus kT. I'm going to use that one, okay? So this one is kT, all right, but this one, that one here, one minus k times t, off period of the main switch. Let's go to the equations. In the meantime, including Yusuf Selim, I'm going to take, it's 20, almost half an hour, so I'm going to take the attendance list. Wait a little bit, please. Evet. Kaydettim. Devam ediyoruz derse. Now, since those slides are directly giving the equations, one equation we have, VA is equal to VS, I come back to, so he says this one is T1, that one is T2. Okay. Biraz daha büyüteyim gene. This duration, T on time, is T1, and this duration is T2. Okay. Yazalım bakalım. That one is T1. That one is T2. İşimize yarayacak, kolaylık olacak hesap yaparken. Şimdi gidiyoruz bir sonraki sayfaya. Next page. So VA, output voltage, is equal input voltage times T over T2. Nereden belli? Since T1 is equal KT and T2 is equal to 1 minus KT, this yields the average output voltage is this one. Vs over 1 over K. K 0.5 is, if it is 0.5, you are producing double the voltage. Output is double. This is output. If it is 0.3, you are producing less than double. But if it is 0.7, K is 0.7, that means longer time you are storing energy in your inductance and less time you are sending it out. That means, let's say it's 0.7, then you are actually obtain 0.3 here. 1 minus 0.7 is equal to 0.3. Yani that means you are actually obtain output 3 times higher, more than 3 times higher than input. It's possible. And delta I is also derived that one. Now I'm going to show you how it could be driven. Follow me, please. I don't know whether you can clearly see it, but Vs is equal to, if it is at on time, L di delta I T1. Burada mutabık mıyız? L di dt. Delta I is I2 minus I1, and this one is T1 on time. Therefore, take T1 is equal delta I times L over Vs. So delta I, don't forget delta I. This is the first definition of delta I. Okay. Now I continue, or T1, calculation of T1. And then the inductor current falls in the second part, that Vs supply minus Va, which is the inductance value. Resme geri dönelim. For this case, for the last case, what is VL here? Output is VA and input is VO. So the difference between those is VL. Where VA minus VS is the LDI dt in amplitude. Amplitude işaretini ben koydum. Bakın. Yani ona dikkat etmek lazım. Çünkü oraya eğer eksi işareti koyarsan delta I zaten negatif. VS minus VA, VS'ten büyük aslında. VA is higher than VS. However, that's the theoretical representation. Is equal LDI dt actually. But DI, if you use DI as a positive value, amplitude, then of course you have to use a minus sign here. Okay, be careful. Then we obtain T2. We obtain T2. Is a function of delta I. Therefore, if you write delta I is equal I2 minus I1, so from the first equation, delta I is this. From the second equation, delta I equal to that. Therefore, VA, So if you solve these two equations and if you put T1 equal KT and T2 equal 1 minus KT, then VA is equal Vs over 1 minus K is proven. This is one conclusion. Output is equal 1 over K VA. So we have already proved that this equation VA is equal. Now we are trying to obtain delta I. What are we going to do? We are going to write delta I was already driven. Bir dakika yürüyelim next page'e. Evet. Şimdi şu çocuklar şu bantı büyütüyorum bakın kolay olsun. Always opposite of the voltage. Şimdi voltage neydi? Voltage was VA was equal K times, I'm sorry, I made a mistake. VA was equal to 1 minus 1 over 1 minus K times VS'ti. Tamam mı? Şimdi current is opposite. Onu da buraya sola kırmızıyla yazayım. Benim anladığım şekilde. IA is equal to 1 minus K times IS. First we have driven that equation. Bu mavi gözünüzü almıyor değil mi çocuklar? Biraz böyle fosforlu gibi çıktı. Görüyorsanız eğer tamamdır. IA de onun tersi. Neden? Çünkü bakın denklem burada. If you neglect losses, YS IS is equal YA IA. Şimdi iki şey bulduk. Şimdi gelelim equation'ları bulduk, çevirme oranlarını. DC transformer. Enes yoklama yaptım. Gidebilirsin çocuğum. Nerede hangi derse giriyorsunuz? Şimdi olmadı bu ya. Nasıl bu kadar çakışma oluyor ki? Hangi ders? Neyse konuşamıyor herhalde. Matematik 1. İyi hadi bakalım. İyi dersler. Sonra bu notları iyi okuyun ha. Bak problem de var çözülmüş hazır. Ona göre. Peki. Şimdi T period is equal 1 over F, which is T1 over T2. T1'ı we deriven already. T2'yu da we have already deriven. Therefore, we can solve those. We obtain this equation. And from that equation, we can delta I is equal, bakın bu from that equation, LVA, Vs over VA minus Vs. This is one equation, delta I. And also, if you put VA is equal 1 Vs over 1 minus K, so if you solve it and if you have Vs here as well, you obtain that equation. Bunu da çıkarttık, tamam mı? Delta I'ı da bulduk. Şimdi ne bulacağız? Capacitor voltage, ripple voltage. What we are going to look at the capacitor voltage. Bunun böyle göründüğüne şey yapmayın. Next sayfaya aldım onu. Buradan okuyarak gideyim. When the transistor is on, MOSFET is on, the capacitor current supplies the load for during the t equal t1 time. The average capacitor current during this time is IC is equal IA. And the peak-to-peak ripple voltage, we assume that capacitor current is constant. Of course, this is an assumption, by the way. Don't forget that. And the peak-to-peak ripple voltage of the capacitor delta VC is VC minus VC time equals 0. So initial VC value. This is VC, of course, VC time. That one is equal 1 over C integral from 0 to T1 IC dt. Bu meşhur bağıntı biliyorsunuz. VC is equal I dt, but you are integrating it from 0 to T1. So I continue from 1 over C from 0 to T1 IA, IC is equal IA dt is equal IA times T1 over C. Buraya kadar tamam mıyız? We obtain delta V with respect to the T1, function of T1. IA is a constant current. This is the final major initial assumption of us. IA is a load current, constant. Now T1, you remember that T1 was already calculated like this. So if you put T1 in this equation here, if you put T1 equal to this, delta VC is obtained IA VA minus VS times V over VA FC. Or if you put VA, if you put here VA is equal minus chi, and IA is equal 1 minus K times Vs. If you put those, put it here, then you obtain delta VC is equal IA times K over FC. Bir denklem daha bulduk. Şimdi bazen durup bir özet yapmakta yarar oluyor çocuklar. Şimdi bitireyim, ondan sonra güzel bir özet yapacağım. O zaman daha iyi anlayacaksınız. I'm going to make a summary. For condition inductor current and capacitor voltage values for continuous induction current and capacitor voltage, the IL, the average inductor current, IL, average inductor current, should be equal to 2 times delta I. Delta I cannot be higher than this. Otherwise, current becomes 0. Okay? So delta I neye etki ediyor? Delta I is a function of, we don't like high delta I. That's why we like high inductance, which means volume, weight, and cost. I repeat, if you make inductance higher, that means you are producing a coil. Görünüyor mu diyelim? So you are actually using a coil, and that's why we don't like that one. It's the cost, additional cost, additional volume, additional weight. That's why we prefer always to have higher frequencies. Okay, of course, uh, we use the proper inductance too, nevertheless. So delta I is a function of those. So if you come back here and make it bigger, delta V is also function of C, inverse. Both of them are inverse function of C. If C becomes high, the voltage fluctuation becomes very low. And if you come here, the critical values for those continuous current case, L should be equal to this value or higher than this. Okay. If L is higher, that means the current is going to be continuous. And also the critical value of capacitor here. Şimdi bitti mi çocuklar? Bakın bitti. Bir problem var. Ama önce ben hadi problemi çözelim. Çözerken belki daha iyi anlayacaksınız. Sonra I'm going to make a summary, brief summary. Okay? Şimdi bir şey fark ettim çocuklar. You see, I'm an experienced lecturer. I'm an experienced professor. However, I'm always learning something. One thing I learned that from my grandchild, if you understand the problem properly, that means it's the halfway to solve it. So I would like to emphasize here that you should understand the problem properly. Okay? So please concentrate. We have a boost regulator. That means we have a boost DC to DC converter. Input voltage 5 volt. And our average output voltage required 15 volt. That means we are increasing the voltage threefold. 3 times input, we are going to get 15. Then immediately you can calculate the K value. And the average load current is assumed to be 0.5 amp. It's constant. You assume that it's a constant. Average means that one. The switching frequency you select is 25 kilohertz. Inductance is given 150 microhenry and C is 2020 microfarad. Şimdi bunlar verilmiş. O zaman ne sorulur? Duty cycle soruyor. It's asking duty cycle. It's obvious. K. The ripple current of inductor delta I soruyor. The peak current of inductor I2, peak current soruyor. The ripple voltage of the filter capacitor delta V soruyor. And the critical value of L and C soruyor. Çok straightforward. Ben galiba geçen sene bu tip problemlerden böyle biraz yamultup sorular hazırlamıştım. Unuttum şimdi. Bakmam lazım. Şimdi başlıyoruz. Input 5 volt. Output 15 volt. Frequency 20 kilohertz. L is given and C is given. Şimdi from K output is equal input times 1 over K. Buradan is K is equal 0.6667. Burayı anladık mı? Yani bu şekle geri dönecek olursak that's right. Input is given, output is given, voltage, and also inductance is given, and the capacitance is given. Those values are given. So first, they are asking K. K burada var. I can find K from here. Sonra ne soruyor? Delta I'da belki bunu kullanacağız bakalım. Bu denklemler bakın 570, 576 denklemler burada. Şimdi gidelim bakalım. Ben denklemleri de burada verdim. Rahatça oradan bakarız diye. Devam edelim probleme. Şimdi delta I neye eşit? 575'ten diyor. Bakalım 575 neyin nesiymiş? ...5.70 kalmış. 5.75 burada. Bu. Bakın. Delta I is equal Vs times Va minus Vs FL Va. Hepsi verilmiş. Yani buraya hatta yazacak olursak eşittir. Problemde. Vs kaçtı? 5. 15 eksi 5. Frekans 25 çarpı 10 üzeri 3. Ondan sonra inductance, eyvah inductance'ı hatırlayamadım. Neyse inductance'ı vereceksin. Inductance'ı yazacaksın. Ondan sonra VA'miz kaçtı bizim? 15'ti. Değil mi? 15'i yazacaksın. Buradan çıkacak. Gidelim bakalım ne yapmış Muhammed. ...15'i yazmış oraya. Gördüğünüz gibi basit. 25.000. Bu da 150 mikrofaradmış. Mikro 10 üzeri eksi 10 to power minus 6. 15'te bu. Yaptığın zaman delta I'yi buluyorsun. Şimdi akımımız ne kadardı? 0,5 amperdi. Continuous. Değil mi? Problemde galiba o verilmişti. Evet. Load current 0.5 amp'ti. Delta I 0.89. Şimdi C şıkkında ne sordu? C şıkkı. Peak current of inductor. Yani I2'yu soruyor. Kolay. I2 is equal IS plus delta I over 2. Burayı hatırlıyorsunuz herhalde. If you remember that. IS 1.5. Önce IS'i buluyor ama. IS'i hangi bağıntıdan buluyor? IS is equal kullandığı bağıntı IS is equal IA times 1 minus K den buluyor. K'yi bulmuştu. It's already obtained K here. So put it here 1.5 amp IS. So 1.5 plus delta I is already obtained, half of it, is equal, maximum current is equal 14945. Minimumu da bulabilir isterse artık. Çünkü minus delta I over 2 dediği zaman da minimum current çıkar. And you can see that it's a continuous current. Bir bakalım isterseniz, kontrol edelim mi? Neyse, boş ver. 1,5 eksi 0,89 bölü 2, 0,09 desek 4,5, 0,4 düş. İşte aşağı yukarı 1,1 amper falan gibi de minimum current var. There is a minimum current is 1.1. Şimdi gelelim delta V'ye. Delta V'nin equation'ı 579. 579'a bakalım. Galiba ben design problemi yapmıştım buradan çocuklar. Mesela L'yi hesap edin. Delta I'nın şu olması için for delta I should be below that, delta C below that, calculate for example ne bileyim L value, C value. It's a design problem. Could be solved. Kaç numaralı denklemde gene çok konuştuk, unuttum denklemin numarasını. ...579. Delta V'nin denklemi. Paydada C var. Besbelli. Frequency var. Şu zaten K. Bu da 0.5. Bir dakika bakalım denkleme. 579'u bulalım. Hangisini kullanıyoruz? Evet, burada. 579. IA K times frequency times C. IA average current is given. Good. Average current 0.5'dı. Değil mi? Gidelim çözelim. Evet, 0.5 times the K value, K, times frequency and times the C value is equal 61 milifarad. Evet. Kritik value'lar. Kritik value equation'larını bir bakın R hesap ediyor, görüyor musunuz? R is equal VA over, problemi bir daha anlayalım. Ripple voltage and filter capacitor peak value and E the critical values of L and C. Şimdi critical values bir tanesi bu. K over 2F R. R lazım bize. We need R. And L also we need R. R neye eşit? V average voltage divided by our average current. R is equal to this one. Average voltage, we know that. Average current is already given. First we obtain R. 15 over 0.5 which is 30. Then L is equal 1 minus K R over 2F. The equation was already there. K is known, and also R is already obtained. You can obtain that one here. And also C, 0.444 microfarad. L kaç? Pardon. 133 mikro Henry L. Bizim problemde kaçtı? Bu da 0.44. Bu 220 idi. Öbürü de L de bundan yüksekti. Nerede L? 150. Gördüğünüz gibi is above those values. Evet. Şimdi Bakbus'ta başlamadan evvel bir 5 dakika 10 dakika ara verelim. Tamam mı? 11:10. Break. Evet, başlıyoruz. Buck boost converter. Önce devreye bir iyice bakalım. Let's have a look at the circuit. In step up, we have to got a coil here. Coil was there and the switch was here. Bir dakika ya. Ok. Ha, tamam. In step up version, we have to get that switch was there and that coil inductance was there. For buck converter, however, the coil was here and the switch was there. Now switch is similar to buck, but this time coil is here. As long as you see a switch, you consider that it is on and off, and consider it's on. If it is on, then the voltage is going to come here. Since this diode is reverse polarized, the cathode is positive. No current is going to flow in this direction. So, however, this one is already short circuit, so there is no resistance. Of course, there is a resistance here. Every coil has got their own resistance, but for this case, just assume that there is no resistance. Current is going to flow and rise linearly. V is equal L di dt, and the integral V is equal integral I dt. Sorry, yazayım buraya da kendim kontrol edeyim. Böyle lafla olmuyor. VL L di dt. So, I'm sorry. Kirchhoff voltage law say that for this case switch is on, yani şu durum, that's the case, current is flowing through that part. Therefore, Vs dt is equal L di. So di, which in your equation is going to be used delta I, is equal 1 over L integral neyse di kalsın o zaman 1 over L Vs dt. So that is the system we are going to use. So it seems that current is going to rise linearly from minimum to maximum. That is the current. That's the current rising linearly. When you reach that point, in that case, you turn the switch off. So what's going to happen? Because of the stored energy, this current is going to flow and charge the capacitor and also supply the load. But nevertheless, these are reference, by the way. Şuna bir ok koyayım. These are reference. Plus and minus reference. In actual fact, it becomes plus here. Burada yazıyor. Bakın plus there. Görüyor musunuz plus? Plus and minus. So your capacitor is charged, but current is going to reduce linearly between off time. In the meantime, by the way, voltage of the diode, bu ne ya? VS. VD nereden çıktı ya? Bu VD'yi ben anlamadım. Deli mi bu? Olmaz. Diyota pozitif gerilim gelmiyor ki burada. Diyota negatif gerilim geliyor. Bu VD'de kabul etmiyorum bu VD'yi burada. Bakın zaten yanlış koymuş herhalde. VC var burada. VC output voltage. Alright. And of course there is a resistance here. Devam edelim biz işimize. If you come down for the second case, in that case, current is going to flow. Current is going to flow in this direction, by the way. So negative current is going to be measured. This is the reference current of the capacitor. So you can see that during on time, capacitor is giving a negative current with respect to its reference. Bir dakika ya, nereden? Ha, bu kapasite vermeye devam ediyor mavi. Kırmızı bu ya. Bir dakika. Renk hatası yaptım çocuklar. Hop, burayı hemen silelim. Bu mavi değil burası. Burası birinci bölge. Birinci bölge. Burada kırmızı renk var. We assume that capacitor is charged. is fully charged, therefore plus is here, plus point here, okay? So supplying current in this direction, IC. And we assume that it's a negative current, bak. It's a constant negative current. But when it comes to the second part, the blue part, for this case, current is going to flow some current store energy and then immediately voltage of the capacitor is going to rise and also the current of the capacitor is going to jump to positive, but in the meantime it's going to be the capacitor current is going to be, while the voltage is getting up, capacitor current is getting down, and at this level, when it becomes, when the capacitor fully charged, it's going to be zero, and then next red part, blue color is our off, switch off time, and the red one is our, so this is the current coming from the inductance to supply the capacitor and the load. But in the meantime, current here, the load current is assumed to be constant. So I'm starting from very beginning. On time, current is going to flow inside the coil, and the current is going to rise, and the capacitor is going to supply the load, and also voltage of the capacitor, since voltage is supplying the load, voltage of the capacitor is getting down. Hala mı abi bu ya? When the time comes and put it off, put the switch off, put this switch off. Nerede o switch? Put the switch off. Then because of the stored energy in your inductance, the current is going to flow through blue one here in the second phase. Buna 1 diyelim. Buna 2 diyelim. Aynı anda olmuyor çünkü. Hangi renk çıkacak? Kırmızı çıktı. Tamam. 1. Mavi de 2. Çocuklar VD dediği bakın. VD dediği follow my cursor please. VD dediği bu noktanın potential'ı. Bu noktanın potential'ı elbette pozitif burada. Yani diyotun katotu pozitif. Ama şurada bunu kapattığın zaman da bu sefer de eksi değere düşüyor ve değeri eksi Vs oluyor. Peki, şimdi gelelim denklemlere. Yani nasıl oluyor da how this device is sometimes become buck, sometimes operate becomes boost. Önce put the switch on. When you put the switch on, what, there is no other device, only the inductance we have. So LDI dt. Vs is equal LDI dt. dt is T1 on time and the di is I2 minus I1. So L delta I over T1. Buradan T1'ı çektik. Tamam mı? T1 is represented with function of L, Vs and delta I. Bir denklem yakaladık burada. Burası kırmızıydı. Gene kırmızıyla göstereyim. Sonra for blue one, when you switch off, inductor current falls linearly. Switch is off. VA is equal minus LDI dt, but time is T2 here. T2 is defined here. Or delta I is equal to, from the first equation is equal to Vs times. Can you follow me? Nobody's responding, by the way. Delta I is equal to, çocuklar bakın şöyle yapmayın. Never do that. Since those notes are already given, I can take the print of it. I can go to the examination room. I can solve the problem or whatever the material professor asks, I can answer it. If you consider that one, if you think this way, it's wrong. When I was student, probably 50 years ago, I was doing the same thing for some courses, and I was doing in opposite in some courses. Those opposite courses, whatever I followed the course together with my lecturer, I became very successful. But when I think that I could read it later, it's all right. I can do it. We'd better take the note now. If you think that way, that is wrong. I start from very beginning. Okay? So fresh up, we are starting. If you switch on, current is going to flow, and we obtain that equation here. And then if you switch off, that's the case. Capacitor is charged, capacitor current is rising, and also but inductance current is getting down. For this case, VA output is equal minus LDI delta I dt. So T2 we calculate. There is always delta I then from first equation is equal to this. For the second equation is equal to that. So if you put T1 is equal T1 is equal K times T. T1 is equal K times T. T2 is equal 1 minus K times T. Then you end up with this equation. So replace T1 and T2. Then delta I is equal T2 is, that's right, VA is equal, we obtain that equation. So if you replace those, you obtain that equation. It's minus, so voltage is reversed of the input. And if you look at the equation, if K equal 0.5, K equal 0.5, VA is equal Vs. If K is higher than 0.5, VA is higher than Vs. Gene çorba oldu. Kalemdeydi. Bir dakika. Baştan yazacağım burayı.
Hocam, if K equal 0.5,
0.5 mı?
yeah,
Evet, devam.
is it going to be VA equal minus VS? Isn't that right?
No, not point 0.15. It's 0.5. Bak.
Yeah, 0.5.
Bir dakika. Just a moment. I'm going to repeat that one. Oh. Tamam. Şuraya yazıyorum. K equal 0.1. VA is equal to kaç oluyor? 0.1 over 0.9.
It's 1/9 hocam. Right?
Neyse yazacağım böyle bırakacağım. 0.1 evet. 0.9 niye küçüldü böyle? Time Vs. If K is equal to 0.5, VA is equal to Vs. 0.5 over divided by 0.5 is equal VA. K equal 0.9.
Hocam, I just have a question here.
Efendim?
Where did the minus sign go?
Okay.
In
Minus.
both when k equal 0.1 and when k equal 0.5.
Tuttum, koydum.
Okay.
Minus. Kaç oluyor? Minus. Bu sefer de 0.9 over 0.9 9 times point. So that one is buck. That one is boost. Siz görüyor musunuz şu anda ekrandaki yazıyı? Yani bir
Evet hocam.
resmi pencerede aç, resmi farklı kaydet falan çıkıyor burada. Size de yansıyor mu? Can you see that one? Resim adresini kopyala. Devamlı müdahale ediyor benim şeyime, yazdığıma, bilgisayara. Ha, Cemile bir şey söyledi. Görmüyoruz dedi. Sağ ol Cemile. Boost. Gene çıktı bak. Yazamıyorum ki, yazdırmıyor. Neyse ya. Tamam, burada görünüyor. Karman çorman bir şey oldu zaten. Şu şeyleri de sileyim. Rezilleri. Nasıl olsa slide olarak açtığınızda böyle görmeyeceksiniz. So it's obvious that uh, you are providing a negative voltage with, of course, the value of K is defining whether your system is buck or boost. That's why it's called buck boost. Şimdi gene malum denklemler. So you remember this equation. T1 is equal KT. So and T2 is equal 1 minus KT. 1 minus K is equal this. And then if you put that one here, T1, T2, and T1 is obtained as a function of frequency, then I1, bana lazım olan bu. I1 is opposite of this one. So K is equal to 0.9. In that case, current is going to rise. If voltage goes up, current goes down. So since input voltage, input power is approximately equal to the output power. That's here, this equation here. Okay. And also similarly, we can peak to peak delta I and delta V can be calculated. Bir dakika ya. Tekrar mı etmişim bu sayfayı acaba? Bu sayfayı tekrar etmişim çocuklar. I repeat that page. 267. Evet, tekrar etmişim. Niye silmedim acaba? Neyse sonra silerim. Now peak to peak inductor ripple current, which is equal to delta I. We already know how to derive delta I equation. So T1 and T2, we have already defined those equations as a function of delta I. So if you write those equations here, then you solve this one and you end up with value is equal to that equation. delta I is equal Vs times Va F frequency L. Şimdi so obvious that the ripple is reduced with the inductance and also the frequency. That's why we increase the frequency. Or that's that simple equation. If you put Va and Vs values, you end up with Vs times K over Fl. Higher the K is the higher the also ripple. But frequency and inductance are decisive here. Inductance current can be easily calculated by using this one. And the peak-to-peak ripple voltage could be calculated by using that equation. IL is equal to, I'm sorry, delta V is equal to integral I dt. Şimdi biraz kafanız şey etti, yoruldu. Onun için biraz bir summary gerekiyor bize. Şunu bir temizleyeyim önce. Şimdi bize ne lazım? What do we need? We have to first learn about the conversion ratio, the function between output and input. We already obtained that it's equal to, we already obtained that VA is equal to minus K to 1 minus K time Vs. This is the one. Current opposite, IA is equal to minus kalsın. Nasıl tanımladığına bağlı çünkü. Kalsın o da. One minus K over K times IS. Tamam, opposite. Since we approximately VA IA is equal IA is equal minus VA IA is equal, neyse amplitude kullanacağım. Amplitude kullanıyorum. VA is equal approximately Vs IS. Enerjinin yönü değişmez çünkü zaten. Enerjinin yönü aynı kalır. Akımın yönü değişir, gerilimin yönü değişir. Okay, so these are the equations, and also we have derived delta I and also delta V equations. We also have derived that one, and we know that this type of network operates as buck boost. Şimdi size bir elektrikli otomobil şeyi vereceğim çocuklar, devresi göstereceğim. Orada mesela bu buck boost kullanılır. Temiz sayfa açacağız şimdi bir tane. Şu Şu DC bus. Plus and minus here. Bu niye küçülüyor böyle ya? Allah kahretmesin ya. Şimdi burada battery voltage var. Şurada. Inductance kullanıyoruz. Burada bir switch var. Buna T1 diyelim. T1'ın daima karşısında bir de D1 var. Şimdi bu devre bir başka switch üzerinden bu devreye bağlanıyor. Bu da T2. T2'nun da mutlaka bir ters diyotu var. Şimdi şu minus'ı sileyim. Minus güzel olmadı. Yeniden koyacağım. Burada bir inverter var. Burada bir elektrik machine var. Bu elektrik machine gear sistemi üzerinden differential'a bağlı. Differential'da tekerleklere bağlı. So wheels, gear, elektrik machine zaten orada. Tamam mı? Enerji, eğer bunun gerilimi voltage of the battery. This one is battery. E smaller than VDC. DC bus of the electric vehicle is higher, and you have to increase if you want to give energy to your system. You give energy to your system. So when you put this one on, when you put this switch on, T1 on, come on, when T1 on, çocuklar herhangi bir şekilde biriniz müdahale etmiyor değil mi? Çünkü şaka olsun diye falan müdahale edilebilir gibi görünüyor bazı şeyler. Öyle bir şey yapmayın, olur mu? So when you put switch on, yapmayın, olur mu? So when you put switch on, then you build up the current here, and then when T1 on, then T1 off, current is going to flow through the DC bus. So on, off, on, off. So you can send the lower voltage, you step up. This is a step up or boost. However, for regenerative braking, since this DC voltage is higher than the battery, then you turn, nereye koyayım onu? Şuraya koyacağım. Şuraya. T2 on, current is going to start flowing from DC bus. T2 on. Bak. If T2 off, what's going to happen? If T2 off, the current is already flowing, and then this current is going to continue through diode D1 on. Anladınız mı? Did you understand that? So you can, for the red one, battery is full, you turn on this battery, turn on this T1 switch on, Onu kırmızıyla göstereyim T1'ı dur. Ben anladım. Anahtarlar kayboldu orada yazıları. T1 off, on. And the T1 off, then D2 on. Since current is flowing, through that diode. If, however, you generally in motoring case, so energy, the red one, that red energy goes through. Nokta nokta yapınca mı küçülüyor, büyüyor? Ne yapıyor bu? Through electric machine, energy flows through electric machine, from electric machine through the gear, goes to the wheels. So torque is produced. Torque, motor, and omega motor is the speed of this one. This is a motoring case, the red one. Tabii buradan hani şöyle pozitif buradan gidiyor da buradan da geri geliyor. Neyse şimdi uzatmayayım daha fazla. Zannedersem anlaşıldı. Either you want in motoring case, you run it as a motor, then the battery voltage is smaller than the DC bus voltage of the electric vehicle, and we produce a boost action. This is a buck boost converter, by the way, boost action, and this is a boost part, and that is the buck part, T2. T2 is used for. Onu da green yapayım bakayım dur. En son kalsın böyle çalışırken belki işinize yarar. Evet, fena olmadı çocuklar. Şekil çok çirkin ama gayet net anlaşılıyor. Green one is regenerative braking while you brake or your electric vehicle is moving in downhill, then energy comes from this part, goes to this part. That is called regenerative braking. Red one is motoring and the other one is braking or regenerative braking or generating. Bu kadar yeter. Şimdi şu problemi çözelim bakalım. Geri dönelim. Biraz da yorulduk gibi. Şu problemi son sürat bir çözelim. Varsa bir problem koydum mu emin değilim. Bakayım ne var elimde. Evet. Evet, boost'u konuştuk bugün. Sonra problem çözdük. Buck boost'u konuştuk. Galiba problem çözmedim. Koymamış. Ha var, koymuş. Hadi şu problemi de anlayalım son sürat. Ne lazım bize? What do we need? We need the turn ratio. We need K. We need current. We need voltage. We need inductance value. If inductance is given, we have to obtain the delta I and delta V. Bakalım verilmiş mi? The buck boost regulator has the input voltage is given. The duty cycle K25, the switching frequency 25 kHz, inductance is 150 microhenry, filter capacitance is 220 microfarad, aynı değerler. The average load current is 1.25 amps. Determine the average output voltage. Onu koyar bakarsın. Eksi 4 volt. 0.25 olduğu için input kaçtı? 12 volttan 4 volta düşürdü. Eksi 4 volt. 1. Bunu yaptık. 2. Ne istiyor? Bu nedir bu? K over 1 minus K değil mi? .25 bölü 1 eksi 0.25 is that one. Şimdi yürüyelim. Average output voltage'ı bulduk. Peak to peak output voltage ripple. Delta V'yi arayacağız. Delta V'nin denklemi 5.95. Hemen bakalım 5.95'e. Evet, burada. Bunu IA'yı biliyorum, VA'yı biliyorum. IA'yı de formülden bulacağım. VA, I already obtained VA. VA minus VA frequency biliyorum, C'yi biliyorum. Hepsini koyacağım yerine. Koyuyoruz. Point 25 bin frekans. Bu da C değeri. 56.8 millivolt peak to peak voltage fluctuation. Current da aynı denklemden, benzer denklemden we have a similar equation for delta I. Hemen bakalım orada. 5.92 diyor. O da burada. Either use this one or that one. Bu tabii daha kolay. Ama K'yi de verdi. Verdi mi K'yi? Dur bakayım. Neyse şunu kullanırız ama. Şurada K yok. Bakayım. Verdi K'yi ya. K 0.25. Tabii canım basit. 12 çarpı 0.25 buradan. So delta I'yi da buradan kolayca buluyoruz. We can obtain. Başka ne istiyor? Ripple in that the peak current transistor transistör akımının peak değerini istiyor. And the critical values L and C istiyor. Bir dakika ya. Burada. Akımın denklemi var. O denkleme bakarak bu K bölü K over 1 minus K değeri. Bu da average current. Average current times this one is giving you the switch current. Peak to peak current of the transistörü de bulmuş bakın çocuklar. Delta I over 2'yi eklemiş. IS over K plus that one. Oradan 2 amper bulmuş maksimum. Son olarak biliyorsunuz önce bir R hesaplıyor. Obtain R. VA over IA is R. 3.2 ohm. Ondan sonra da bağıntılar belli zaten. 2 tane bağıntı var. You put those and obtain those values. Şimdi bir ara daha vereceğim çocuklar. Çeyrek geçe buluşalım mı? Bir şöyle kalkalım, dinlenelim ve hatta 20 geçe buluşalım. 11:20. 11:20 break. Okay, see you then. Hello again. Can you see that? This is a typical electric vehicle where, are you there, by the way? How many students do we have? We have only 15 students. Okay. So this is a typical electric vehicle. You can see that one here is a famous DC bus. This is the fundamental major design factor to define the voltage of this one, DC bus. And this DC bus is connected to supplies to an inverter. An inverter produce uh, frequency control, speed control, voltage control of electric motor, therefore torque control. Torque is produced by electric motor and the speed, rotational speed, through the differential is connected to the wheels. Okay, and that is the battery pack. Quite often, a DC to DC converter is connected between that one. Here, for this example, battery voltage is equal to the DC bus voltage. If it is not equal, I have already given you buck boost converter to be used. And quite often it is used. Now, what's happening here actually, we would like to charge this system. For this system, you have either single or three-phase AC supply. So you have to convert it to DC. Okay? When you convert it to DC, then there is a funny device here which is called a power factor corrector. This power factor corrector actually is used to reduce the disturbance effect caused by this system to your supply. That is grid. Grid means if you are in your house, that is your plug-in connector, and grid means your three-phase system, probably 400 volt, 50 hertz system. But sometimes there are uh, fast charging mechanisms. Fast charging means that you directly give DC current to the DC bus. High DC current you give it. Okay, so therefore power in that case is much higher. You need a three phase. Now I'm going to give you the role of this power factor corrector. Okay, I'm going to explain it to you right now. While I open this material, I also would like to show you this one. If it is a fuel cell, if you use a fuel cell is a device which gets hydrogen in one hand, oxygen in another hand, and then there's a membrane, there's a particular part of the fuel cell is called membrane. In membrane, these two, oxygen and hydrogen, comes together, and then electrons are produced, and also water is produced and heat is produced. So the fuel cell actually is used, taking the hydrogen as a oxygen is already available in the atmosphere, but gets hydrogen and produce electricity. Quite often, we also use supercapacitors to supply the DC bus. This one is a battery pack, and then you can see that how many DC to DC converters are used in order to supply the DC bus of the system. So these are the examples of those. For hybrid electric vehicle, that these are the what's going on. That is hybrid electric vehicle. That these are the what's going on. That is, you can see that this is the one I described. This is a buck boost converter. Although they call it boost, but it is a buck boost. Regenerative braking is possible too. If you turn this switch on, current is going to flow. Red değil mi current? Current is going to flow through that network. And energy is stored in inductance. And when you put it off, then this current is going to be transferred to the DC bus. So if DC bus voltage is higher than the battery voltage, which is the case here, you can see that this one is, for example, 400 volt, 600 volt, this DC bus. This DC bus has got 400, 600 volt. And if you have 250 volt battery voltage, then you can send energy by using the boost. But buck also is possible. This switch might be used for buck operation, for if you produce electricity with that generator, and then generator produce electricity, and then you send it to the green one. Onu da koyayım bari. It's called regenerative braking. That is the network, okay? So this is regenerative braking. That one is motoring. Evet. Bu kadar yeter. Evet. Burada da anlatmıştım ama bu başka bir dersin notu. Geçiyoruz, bunu kapatıyoruz. Çıkıyoruz buradan. Tekrar kendi ders Muhammed Raşit's course material we come back. Sorry. O daha var bayağı. Biraz daha gidelim. Geçmiş. Evet, bak boost'u yaptık biz. Ne kadar çirkin görünüyor ya. Onu sileyim şunu. We completed the buck boost and then we already obtained the inductance value, current variation, conversion ratio, buck case, boost case, delta V, voltage fluctuations and things like this we have calculated. We solved the problem. There's a converter called Chug converter. Chug converter çocuklar, you are not going to be responsible. And there is also SEPIC. SEPIC nerede ya? Ha. There is also SEPIC converter. You are not responsible either. We recently developed a SEPIC converter for an industrial company. They were using in bus illuminating systems is a DC system, and they would like to control the DC voltage for LED illumination. I think, as far as I can remember, and system should provide a pure, equal, constant DC voltage. SEPIC converter. Two control switch are used. You can see those switches. SEPIC. Chug and SEPIC converters are similar, but in industry you may also have to work on this one if you join the industry. You are not responsible. That's the one I'm going to explain first. You remember that in battery charging network, this assume that this is a DC bus. Assume that this is a DC bus, and assume that you have a diode rectifier, single phase. You are charging your current with a slow, for example, at night between 11 o'clock at night until morning, 8 hours or something like this. So, however, we use that network here. Since DC bus is controlled by a capacitor, there is a voltage here. If you have a voltage there, bakayım ikinci sayfada bir şey var mı açıklayacağım? Yok. O zaman bunu benim açıklamam lazım. Şimdi çocuklar, basit bir şey. devre. Now, output voltage is going to be output voltage is going to be this is your supply. This is time or omega t, and this is Vs supply. And now rectification, of course, is different. Rectifier output is something like this. Positive part, negative part, again positive part. So this is the one. But assume that voltage here, that voltage here is biraz büyüteyim bakayım, göremiyorum. Bir output. Output voltage is something like this. Since capacitor is charged, output voltage is something like that. The output. So current actually, since current is flowing, current actually is something like this. Is going to be something like this. But for supply current, by the way, IS is going to be something like this. This kind of current we don't accept. You can't draw a current from your, you can't draw a current like this from your supply. That is the current IS current. We can't accept that current. This current is very bad. The crest factor is very high. So what are we going to do? What we use is called boost converter or boost rectifier. Sometimes it's called boost rectifier. Industride duyacaksınız bunu. Boost rectifier. Çok kullanılıyor ha. Onu söyleyeyim. It's widely used. Now, şimdi başka bir renge geçeceğim. When you turn the switch on, Okay, current is flowing like this. Actually, we are storing energy in inductance. So current is going to rise. The supply current is going to rise. But when this current rises, we are not happy. We have to turn it off. When you turn it off, it goes down. Then put it on again. Turn it off, put it on, turn it on, put it on, turn it on. So that's kind of current we draw from network, which is very near to sinusoidal. Because of that turn on and turn off action. I'm sorry, I made a mistake here. Okay, so this, did you understand what's happening here? Bunu anlamanızı istiyorum çocuklar. Bakın, we keep this system, we have the voltage here and the reference voltage, we control it. We would like to keep the voltage constant, by the way. Because of the capacitor here, the voltage is going to be kept constant. And then the controller we use, and then voltage and current converter is compared, and the firing signal is given to device. When you turn this device on, the purple current, pink current is going to flow, and current is rise. If you do not turn it off, current is going to be, çiziyorum bakın, böyle gider. Infinite'e doğru gider. Ama biz, in order to keep it, we keep it inside the hysteresis band. We define an hysteresis band. So if current reach a maximum band level, the comparator. So if current reach a maximum band level, the comparator will tell us that and give a firing signal, draw the firing signal and turn the switch off. When this switch off, then current is going to, because of the stored energy in your inductance, current is going to reduce. That is the one here. Then current is going to again put it on, current is going to rise. So put it on, current rise, put it off, current rose, reduces, increases, reduces, increases, reduces. In the meantime, we managed to get this average. So this switch must be a high quality, high frequency switch, most like the MOSFET. So we obtain that hysteresis band. You can see that. You can see the average value of this one. This is called boost rectifier, widely used in charger networks or widely used in even in three-phase rectifiers. I'm going to show you the next page. For example, this one. You can see there is an inductance, either source inductance we use, or we add an inductance in front of the system, and then only one switch is capable to do that. So we know that the three-phase network is something like this, but in order to control the current near to sinusoidal, we use that switch. Mesela bu ilave bir enteresan bir transformatör, zigzag bağlı bir transformatör konuyor. Inductor konuyor daha doğrusu. Ama birinin coil'ı öbürünün birinin core'u, one of the core is also connected to the other core. And that switch is controlled by, so you are comparing the value here. There's a divider here. So you measure the voltage here. You can see that. That's a practical network. Bakayım başka ne var burada? Yok. Modellemeye falan geçiyor buradan sonra. Evet. Şimdi çocuklar, önümüzde 2 haftamız kaldı. Bakın, bir şeyleri görmedik. Flyback, forward falan bunları görmedik. Ama we have already learned about the basics of those. And we have to also learn about the inverters as well. Next week, we are going to start inverters. And then the week after, probably we will be discussing. So you have already got problems solved for DC to DC converters already in your book. So if you download Mohammed Rashid's book, there are other problems in it. Okay. So I think I'd better terminate the course now. Bakayım başka neler var burada. Bundan sonra you are not responsible from the rest of it. These are modeling techniques. Bak. SEPIC converter model. Fourier analysis is going to be necessary for you as well. Input filter, output filter. In your engineering life, you may need those information. However, for the course material, because of the time limitations, we are not covering the filters. Okay. Okay. I have already got attendance list, so you can now leave the course. Thank you for attending. Thank you for listening. Bye bye all.